Hello, my name is Sean Sadler. I'm here with Dilla Biswal to talk about composable data processing. First, an intro. I'm a principal scientist at Adobe Systems, and I've been working on the Adobe Experience platform for about 2 years. Dilla started more recently in 2019 as an architect, and he's also a contributor to Apache Spark. So first, we're here today to give a story about scalability, not in terms of throughput, but rather the output of our engineering team. First, we'll talk about the why, and we'll provide some context around the Adobe Experience platform, around our team, and some of the problems we have faced. We'll talk about the what by walking through the CDP design. Then we'll get into the how. Dilip will talk about the nuts and bolts around the different data processing techniques that we're using in CDP. And finally, we'll talk about the impact the CDP has had on our team, on the platform, and our customers. So AAP is a platform for driving real-time personalized experiences. And we do that by making data actionable. And you can see that in the diagram above. First, we have data, which is about people, places, events, and things within your domain. Then we have semantics and control. That's data governance, about controlling and managing how your data is used. Third is intelligence, and that's about custom or out-of-the-box machine learning models to enrich your data. And finally, we have action, whether it's providing targeted ad campaigns or a better web experience. Adobe AAP provides applications to enable those experiences. Now, how do we do that? We have a suite of applications from Adobe Analytics, Audience Manager, Campaign, Target, Experience Manager, Magento, Marketo, and more that's built on a set of intelligent services. On top of that, or below that, we have Adobe Sensei, and then we have the data that's collected through Adobe Experience Platform. It's that last piece that both Dilip and I operate at. So we're both part of the data ingest team for ingesting data into data platform called Siphon. And the Zen of Siphon is about enabling producers to send chunks of data called batches that we make available to downstream consumers. Now, it's not all about moving bits around. We also need to apply transformations to that data, taking it from raw form into an optimized format like Parquet. It's also about validation. We need to apply validations to a target schema, which we call the experience data model. It's also about partitioning, ensuring that we can have an optimal access for different data access patterns. Compaction to support sources that have high frequency small files. It's also providing an exactly once guarantee to make that data durable without duplication. And finally, lineage tracking, so we can track the who, what, where, and when of the data that's been produced. Now, even with all that said, at this point in time, we're early on, we're still processing about 1 billion batches per day. That's 13 terabytes, and equates to 32 billion events. So our focus has been on cross-cutting features. And what I mean by that are those features you would find across any big data application as you would expect. Things like queuing and throttling. To handle spikes in workload. Also scaling based on backlog and or utilization. We also need to break across workloads, across different bulkheads to support the cases of either having back pressure and or poison pills that could bring the system down. We support logging custom metrics for monitoring, alerting, and to notify downstream consumers that data has arrived. And then there's ability to execute these distributed big data applications across a runtime like Databricks. And finally, resilience. We need to ensure that those 1 million batches are taken to completion or that we're alerted within a given SLA. Our focus in 2019 has been on hardening these features for a minimal feature set. But 2020 is changing. We're being asked for a lot more features. Things like supporting a number of additional raw ingest formats outside of CSV, JSON, and Parquet. providing additional ETL transformation capabilities to go from raw data to XDM. Provide additional validation capabilities, such as format checks, range checks, even context-specific checks based on where the data is going to land. We're being asked to provide additional diagnostic and reporting tools. We're being asked to provide alternatives on how and where you can write the data to. And finally, there's many opportunities we have in terms of tracking, managing, and mining, and providing auto-correction features around failed or bad data in the system. Now, considering all these different concerns that we have, we could have different sets of people, different teams working on each of these concerns. Unfortunately, there's only a single team working on these data processing features, and that's Siphon. And we're stuck with this zero-sum game, where we have more resources working on cross-cutting features. If we move them to data processing, we have to take away from the hardening work we're doing there. Unfortunately, we have requirements coming on both sides of the scale. The challenge we have is how do we increase the amount of data processing features that we have while not compromising the stability of the system. So we've looked at several options. Option A is a path of least resistance. This is really just coding to it. But it means that we need to deprioritize the hardening work that we're doing. It also means that developers will be working both on those cross-cutting features and the data processing features, resulting in context switching, which is overhead we prefer not to incur. Overlapping those concerns can also lead to spaghetti code, making it increasingly difficult to test over time and increasingly difficult to maintain over time as well. Therefore, we moved on to also look at option B, which is more of passing the buck, right? So rather than having a single pipeline, we break up to have multiple pipelines, leaving this initial Siphon pipeline untouched. However, this leads to a lack of reuse. All those cross-cutting concerns that we had with Siphon now need to be duplicated in each one of these services. This also leads to a lack of consistency because each one of these services may have different SLAs, different delivery guarantees, or different validations. This makes the end-to-end testing more complex, results in a more complex monitoring as well, and complexity that will build up over time. However, since we have multiple steps involved here too, and multiple output paths, so we result in increased latency and increased costs. So this led us to look at option C, which is composable data processing. We kind of want to have our cake and eat it too here. So we asked ourselves the question, what if we allow these other teams to plug into Siphon? This will allow us to scale our engineering effort, modularize our design and code. We can also provide a clear separation of responsibilities. It'll be easier to test the system, easier to maintain, and it'll maximize reuse. And by having a single step, a single pass through the data and a single output, we're going to end up benefiting with a minimal complexity, minimizing latency, and minimizing the COGS. And so what we've done is we've taken that zero-sum game and made it a win-win game. This leads us to the what. And we're going to talk more about the option C. We need to implement a framework that enables different teams to extend Siphon's data ingest pipeline. So at a high level, what we need is raw data as input, and we're showing that on the left-hand side, and a target schema, which we're showing on the right-hand side. The intent of the framework is to transform that raw data into something that fits into that target schema. So in what does make it over needs to go to the data lake, and what doesn't make it over needs to be quarantined. So we need to do things like map name over to first name, last name. We need to map the B-day over to the birth date of type date. And we need to map that level over to rewards level, which has an enum constraint defined on it. This is going to require multiple steps. But the first stage is parsing. We're going to take that raw data as input and translate it into a raw data frame. However, not all the data makes it over. And we can see that we have one record that fails. It's because it's corrupt data. It's missing an ending bracket. we need to record that fact into a separate error data frame. That gets us to the second stage, conversion. The input to this is going to be the raw data frame. We want to translate that into the target data frame based on the target schema. So you can see that the name has now split out to first name, last name. The birthday has been mapped over to birth date. However, once again, not all the data has made it over. The second row with ID3 didn't make it over because it has an invalid date time string. We also need to record that in the error data frame as well. The third stage is validation. So now the input here is going to be the target data frame, but now we have some invalid data we need to also filter out. And we can see that it's the second row here with ID4 that's invalid. The reason is because of the rewards level field that has an enum constraint. So that value needs to be one of bronze, silver, or gold. So the fourth stage, we now have the target data frame with valid data. We can simply save it to data lake. And in the fifth stage, things get a little more interesting because we now have a set of error data frames that we need to union together. And we want to join that to the initial raw data frame, write that data out to quarantine so that clients can diagnose issues and or correct data. Finally, we've looked at all the components and the various responsibilities. These are implemented within the Spark driver running on top of Databricks. I'm going to pass over now to Dilip to give more details around the plugin runtime.
Thank you, Sean, for giving a very good high-level overview of the problem we're trying to solve. So we'll now look at some of the implementation challenges in detail. I will start by discussing the DSL that drives the execution of various plugins, which are responsible for either converting or validating the data. We'll go through the APIs or the contracts between SIP and the plugins. Next, we'll look at the processing of the three different kinds of errors, the parsing, the conversion, and the validation errors. We'll then go through a small illustration that shows how the three different kinds of errors are consolidated into a common error schema. Finally, we'll look into the details of how these errors are generated and captured at a row level. All right, so Siphon Ingest Plugin Framework, or SIP, performs the task governed by a DSL. We can also think of it as a set of dynamic configurations based on which SIP does all its actions. So in this case, we can see that the processing of the input CSV file goes through various stages. First, it is fed through a parser, then a set of converters and validators, while capturing the errors in each of the stages. At the end, the surviving rows, or the rows that are free of errors, are written to the data sink, and the cumulative errors are written out to the error sink. The data sink and the error sinks are basically persistent stores like ADLS or Cosmos DB. So in the interest of time, I'm not going to get into the details of these APIs or the interfaces, but I'm going to touch upon some of the key points. So firstly, both the converter and validator take a data frame as an input and return the results. So a converter returns both the success and the error data frames, whereas the validator returns just the error data frame. The reason for this difference is the output of the converter may be of different schema than the input, whereas the validator works on the data that is already converted. That is, the data is already aligned with the target schema. I'll discuss this more later in the talk. So with this background, let's look at each of the error in detail. First, the parsing errors. So one thing to note here is that the parsing errors are applicable for only text-based formats such as CSV and JSON, and are only processed by SIP at the beginning of the validation process, because we want to get rid of the parsing errors as early in the ingestion process as possible. Here, we completely rely on Spark to detect the parsing errors, as Spark is the compute engine that reads the data. So with that, let's take a look at some of the examples. So, actually we have two examples here. One is for JSON, one is for CSV. But the CSV case is actually a little more interesting because we need to pass some extra information to Spark, whereas the JSON case is pretty straightforward. So let's focus on the CSV case in the interest of time. So we have two rows. The second row is a problematic row because it has an additional column that does not conform to the schema. The schema has two columns, name and age. So in order to get the parsing errors, we need to provide Spark with the read schema, Here we see that we have added one extra column called underscore corrupt record, which will be used by Spark to store the parsing error. And in the read options, we see that we have instructed Spark to use the permissive mode of parsing. And also we have supplied the column name of the corrupt record. So with this two extra piece of information, when we read this file, Spark will produce a data frame that will look like the one in the right. Here we see that we have got an additional column underscore corrupt record, which actually captures the parsing error. With this data frame, if we can apply a simple predicate on the corrupt record, we can actually find out the good records and the bad records. So now to the converter and validation errors. So once we have processed the parse errors, the surviving rows are subjected to conversions and validations. So here again, using the DSL as the input, SIP determines the list of converters and validators it needs to invoke and calls upon them in a sequence. So a converter plugin collects and computes both the output rows and the error rows, and only the good rows are passed to the next plugin in sequence. This is because if we do not convert a row to conform to the target schema, then there is not much point in examining that row any further. But this is different in the case of validator plugin in that even though a row is rejected by one validator plugin, it is still examined by the next validator plugin in the chain for us to be able to collect and report all the possible errors in the data. This is to minimize the number of round trips a user has to make in order to get his data ingested into our system. So with that, let's look at a small illustration that shows how we consolidate these different kinds of errors. So we start with the input data and we apply an expression called monotonically increasing ID, which is basically to assign a logical row identifier to each of the row. Now let's imagine we have a conversion that looks like the one that is shown in the mappings table. Here we have a mapping rule which says that we have to concatenate the first name and the last name column, and the target column is going to be full name. So here I would like to say that this is a very simple example of how a converter may look like. But in real life, actually, different plugins or different components that Sean mentioned would actually implement their converters using their custom rules and mappings. So once we apply this mapping on this input data, we see that we produce two data frames. One is a success data frame and one is the error data frame. We see that the row record with row ID 2 is rejected because the last name field is null, and that is not accepted in our system in this example. And the success data frame has two rows, the row ID 1 and row ID 3, but we do see a problem with the second row because A's column is negative. But that is not a concern of the converter at this point. We'll see how a validator processes this row. So now we take the output of the converter, the good rows, and we apply a target schema on top of it. In the target schema, we have defined a constraint which says that the age has to be positive. So when we apply this target schema on this data, we see we see that we have a error data frame, and the record with row ID 3 is rejected because age cannot be negative. Now at this point, we have both the conversion and validation errors. So we could at this point apply a simple relational union operation to combine these two errors. So one thing here to note is that just like we standardized on the API and the interfaces that we talked about earlier, we also have standardized on the schema of the error. That means all the plugins and the components actually return the errors using the same schema. Therefore, we could combine these two data frames using a union operation. So we have now the cumulative errors, and we see that if we just apply two basic join operations, we can compute the final error data frame and the final success data frame. When we take the original set of rows where we applied the where we generated the row identifier, we take those rows and we join that with the cumulative error data frame. On the join column being the row identifier, it actually produces the final error data frame. we can see that the final error data frame contains all the input columns as they were sent from the user. Because the data that the user sends to us may not have a natural row identifier, by sending all the input columns or the input column values, it hopefully provides enough context to our users to identify the rows that are problematic and fix them and resend. So to generate the success data frame, we take the output data frame, that the success data frame that we got from our converter, and we do anti-join. Why do we do an anti-join? Because we see the second row, which was having age column, negative age column, actually was rejected by the subsequent validator, and we must exclude that row from our output. That's why we need to do an anti-join between the success data frame from converter with the cumulative error data frame on the same join ID column, that is row identifier, to get our final success data frame. So once we have these two data frames, like Sean mentioned, we could write them into a configurable sinks, any error sinks. So at this point, we have looked at the three different kinds of errors and how they are consolidated, and how they are basically, how do we compute the success and the error data frame. But how does this error get generated in the first place? So most of our existing conversion and validations actually make use of UDFs. So prior to introducing this plugin architecture, we used to do data validations and data conversions, but we used to work in a fail-fast mode. That means when the first error occurred, we used to fail ingestion and report the very first error to the users, and that is what we are trying to solve as part of this work. So, we needed a way to be able to trap these errors at runtime and proceed to examine the next row in the sequence. So, and the second thing is that our data was based on heavily nested type. I mean, was nested types. Therefore, we had to write the nested UDFs. And currently, it is not possible to capture the errors from the nested UDFs the way we want. That's why we introduced these custom expressions that help us to trap the errors. Now let's look at how these custom expressions look like. So it's a simple expression, as we can see, that extends from a unary expression, which means this expression has got one child, which is a expression itself. And then second thing is that the output of this expression is actually a struct type, and it has input column, output column, and the error information. The input column is nothing but the input that actually is passed to the child expression, input to the child expression. And then the output column is actually output of the child expression. And the error information obviously is whatever the errors that happen during conversion and validation. With that, okay, so now let's look at the evaluate method, which is again very straightforward. We call upon the child's evaluate method, but we wrap that in a try catch block for us to be able to trap the errors. So when we see an error, we actually save it in these variables, error message and error name. And finally, we wrap them, the result, in an internal row and send it as a return value of this expression. Okay, now let's take an example. Let's take an example and see. We have an input data frame which has two rows and two columns, name and age. So we print it out. We have a problem with the second row. We are going to see how we are going to trap the error. So we take a small UDF which simulates how a validation UDF may look like. That takes an integer as input, and it checks if the value is negative, then it throws an exception. And for us to be able to show the output value or output column of this error trapping expression, I multiply the input age by 2. Okay, here we create this custom expression, and we can see that its child is actually this validating UDF, which is age UDF. And now when we map the age column and we attach this newly created expression with the age column by calling the with column API, and then execute this data frame, we see that that the errors are actually trapped in the second row. The first row, we see that we see both the input and the output column. Input being 30 and output is 60 because we multiplied it by 2. but the error information is actually null because we could successfully convert this row. Whereas the second row, we had a problem converting, therefore we don't have an output column value, which is null, but we do have the error information. And then I print the schema to just illustrate that the age column's type actually has changed from int to struct. And under that struct, we store all this input, output, and error information. So with the data frame schema, the way we saw, we could easily compute the error and the success data frame. To find out the good rows, all we have to do is to look for rows where age.error code is null. Similarly, to find the bad rows, all we have to do is to look for rows where age.error code is not null. So that's how we trap the errors and we filter out the good rows and from bad rows. With that, I'm going to hand it over to Sean to share his final thoughts. Thank you, Sean.
So remember that zero-sum game? We had the trade-off between data processing features and stability? Well, that's no longer a problem. With CDP, we now have other teams, 3 other teams in fact, that are contributing not just code, but components that can enhance the plugin framework for Siphon. And this leads to many benefits for us on the Siphon team. We have scalable engineering. We have a clear separation of responsibilities between those working on cross-cutting concerns, us, and other teams that are now working on data prep and data validation. We have more readable code at the end, more testable code, and it's easier to maintain. If we look at the benefits for platform, we actually need to take a step back because we initially had taken that option B, meaning passing the buck, where we had multiple connected pipelines. But the thing we did notice is because we had to pass over the data multiple times, we had an increase in latency. We also had a significant amount of storage costs and compute costs. It just wasn't tenable. With CDP, we've solved that problem. Now for our customers, what it means is that we can deliver more features faster for ETL, for validation, for error reporting. More importantly, the overall experience for the average file size that we have going through these more complicated flows, we're down from minutes to seconds in execution. So this does end our session. What we hope you get out of it is 2 things. First, think about extensibility in your software project and how it can help you scale your project and your development. Second, also leverage some of the data processing concepts and techniques that Dill talked about in terms of how you deal with failed data. Thank you very much.